Okay. How many biological parents do you have? Yeah, it's two. You're right. Yeah, this is an unwaivable law of nature. We all have two biological parents. How many biological grandparents do you have? 4 is the most likely number. How many biological great-grandparents do you have? Okay, yes, okay. And as we progress up the powers of 2, the fuzziness of that number grows. So if we go back 10 generations, you should have a maximum of 1,024 ancestors at that level, but it's actually quite likely that you have less than that. And if we went back 20 generations, the maximum is 1 million possible forebears, but it's almost certainly not 1 million. By the way, if we go back 10 generations, that's about 400 years. So now we're back in the 1200 ADs. Let's go back even further. Let's go back 30 generations to 800 AD. You would now have 1 billion possible forebears, but there weren't 1 billion people at that time. So no way did there's been some mixing going on. Go back another 400 years to 400 AD, and now it's 1 trillion possible forebears, but there have never been 1 trillion people ever. So this curve, which starts out at powers of 2, starts to curve inwards. It doesn't make it all the way out to the powers of 2. And in fact, there's another mathematical thing going on here. As you go farther and farther back in time, the odds that someone who lived before then's line died out is positive. The farther back you go, the more likely it is that some line died out. And it is a mathematical certainty that if you go back far enough, every line has died out except for one. Which means that all of us in this room and every person on the planet ought to be able to trace our lineage back to a single woman and a single man. This is a mathematical certainty. I'm not talking about some religious thing, right? It's just a mathematical certainty. Somewhere in the deep, dark past, there is an Adam and an Eve from which all the human genetic material has derived. And we know something about these people, remarkably enough, because there is evidence within our bodies that is preserved through the ages. Most of us, well, all of us actually, have within our cells a little bit of DNA that comes strictly from your mother. It's called mitochondrial DNA. It's not carried in the nucleus, it's carried in a little organelle called the mitochondria, which is responsible for transforming glucose into energy. The mitochondrial DNA you got from your mother, because the eggs have it, the sperm don't. She got it from her mother, she got it from her mother, she got it from her mother, who got it from somewhere back in time, from the mitochondrial Eve. Men in the room, you got your Y chromosome from your father, who got it from his father, who got it from his father, who got it from his father. So somewhere deep, dark in the past, there is the Y chromosome Adam. And we know a little bit about the mutation rates. We know how rapidly, roughly, these bits of DNA change over the eons, so we can date when these two people might have lived. And it turns out that the mitochondrial Eve lived 70,000 years ago, roughly. And that was the Y chromosome. Adam, he lived 70,000 years ago. The mitochondrial Eve lived 120,000 years ago, before the last ice age began. The Y chromosome Adam lived about 70 million years ago in the midst of the last ice age. And we also know the location. They were both apparently born in the east of Africa. And we know this because of the amount of genetic diversity that lives there. So I think that's fascinating, and it's not what I'm here to talk about. Do you remember the 80s and 90s? Some of us do. Probably quite a few of us do. In the 80s and 90s, we had heroes in the software world. And those heroes looked something like this. That's Grady Booch. Who remembers Grady Booch? Yeah, Grady Booch. And why do you remember him? Because who could forget those two words? He's got a great name, Grady Booch. Now, he wrote a good book, right? A couple of good books, actually. I've got it up on the board there, Object-Oriented Analysis and Design with Applications. Who read this book 20 years ago? Yeah. And what did it tell us? Draw clouds. Okay, we forgot about the clouds now. We're not going to do clouds anymore. But we did learn about objects and relationships and inheritance and using relationships. And he painted this lovely picture of how to do design and architecture. And that's what we were all about in the 90s, in the late 80s and the 90s. How do you get the right design? How do you get the right architecture? Remember that guy? That's Jarnes Trustrup. He wrote the language, C++. Why did he write this language? Why did Jarnes Trustrup write C++? What was he programming before he wrote C++? Simula. Yes, he was in Edinburgh. He was programming in Simula 67, the first object-oriented language. And then he got hired by Bell Labs, and they said, you should write in C. And he kind of went, oh, no. And he wrote a little preprocessor that sat in front of C. He called it C with classes, that made C look like Simula. And then that grew into C++. And all of us at this time were interested in how we were going to do objects. C++ was the language we were going to do it in. And we were going to use Grady Booch's ideas to do it. We were very enthusiastic about design and architecture. And then along comes this guy, Ivar Jakobsen, who writes this really tremendous book, Object-Oriented Software Engineering, and he introduces to the world the concept of use cases. Who remembers use cases? Now, I'll tell you what happened to use cases. Use cases, wonderful idea. I'm going to go back and talk about them in a minute. But what happened to them was the invasion of the consultants. The consultants came and thought, ooh, this is a good idea. I bet I could embellish it. And they did. Who remembers downloading PDFs of use case forms that were page after page after page of fill in the blank crap? The title of the use case, the primary actor of the use case, the secondary actors of the use case, the tertiary actors of the use case, the preconditions and the postconditions and the first primary course and the second primary course and the alternate courses. And of course, you look at all that and say, I've got to fill all that out. And then, while we were in the throes of all that, 1995, design patterns, the gang of four, the guys who brought this semblance of order to the apparent chaos. 24 design patterns that will live in immortality. We thought there would be many more. We thought this was the first of an avalanche of design patterns. It didn't turn out that way. A couple more showed up here and there. And a few people wrote a few more books with a couple more design patterns in them. But these 4 guys captured probably about 75 to 80% of the design patterns that people use on a regular basis. And now we had all the tools. We had everything. We had the language, C++. Well, Java was coming. And okay, we had to deal with that. But in Java, if you squint real hard, it's still C++. And we had all the object-oriented design tools, and we had the design patterns. We had it all. And we were ready to go. And then the focus changed. Now it's going to be code. Who remembers this book? Who's read it? Oh, it's almost the same people. Good. I remember reading this book in 1995 or 6. No, 98. My son was playing hockey, and I would take it to the games. And the great thing about hockey is that your son cannot be on the ice for more than about 5 minutes because they get too tired and they have to come in and sit down, so the coach sends other people out. So while my son's on the ice, I'm watching, and then as soon as he sits down, I'm opening up the book and reading this book. And I remember this is the first book that I ever read that presented code as something malleable. Every other book showed the finished product. This is how you should write the code. And any programmer would look at those books and go, it never looks like that when I write it. There must be something wrong with me. And then Martin puts this terrible code in the first chapter of his book, and it looks very familiar. Yes, I've written stuff like that. And then shows you how to manipulate it and twist it and turn it into something wonderful. And he implies, but does not quite state, that you need unit tests in order to do it. That was clarified by this guy, who came along and wrote the Extreme Programming book. Now we're into 1999. I was here at OOP in 1998. Kent Beck was teaching in the room across from me. I was teaching a C++ object-oriented design thing. He was teaching, I don't know what, something. And I walked into his room at a break and I said, you know, Kent, you've been writing about this extreme programming stuff. It makes no sense to me. Why don't we sit down at lunch and talk about it? And he sat down with me at lunch and we started to chat, and I thought, you know, this is getting pretty interesting. He's got some interesting ideas. At the time, I was the editor of the C++ report, so I asked him to write a column or an article for the C++ report, which he graciously did. This was the height of sacrilege, because Kent Beck was a Smalltalk programmer, and I was letting a Smalltalk programmer touch the hallowed pages of the C++ report. It was a great article, too. So now we've got the process. We've got the designs, the tools, the patterns, the use cases, the process, the focus on code, and then the Agile Manifesto. Bunch of guys get in a room at Snowbird, and we write down these 4 rules. I don't remember who it was that came up with the 4 rules. I think it was Ward Cunningham, but he denies it. But there they are, the 4 rules. Individuals and interactions over process and tools. Working software over comprehensive documentation. Customer collaboration over contract negotiation. Responding to change over following a plan. It's not that the things on the right are bad. They're not. It's just that we like the things on the left better. The people who signed it, you can see on the bottom, that group has never reassembled. We almost reassembled a few years back at the Agile conference, but a few were missing. And even then, we didn't like it. These were people who fundamentally disagreed about everything except for this one day, this one occasion, where some kind of magic happened. And we managed to put this together and go our separate ways and never meet again. And of course, we also got that. How many here are doing Scrum? Oh, look at that. Lots and lots of Scrum. Good. We like Scrum. Scrum is fine. Well, Scrum is okay if you do it right. Of course, that's true with anything, isn't it? And the memes began to spread. Courage, no big upfront design, who came up with this idea of no documents? Goodness gracious. You aren't going to need it. Simple design, all of these ideas roaring around in our minds, in our heads. We were poised to do great things. It happened overnight. None of us expected it. The bubble popped. All of a sudden, all of our great momentum was just thrown into a permanent stop. The brakes had been applied. We screeched to a halt, and we wondered, what the hell happened? And now we were in a different mode. Now, if you had a job as a programmer, it was a rarity. These guys were actually fairly common. Now, that's obviously a guy who's pulling a joke, but there were a lot of unemployed programmers during that time. And we took on a very different attitude. And that took place in the midst of the web, growing and growing and growing and coming to dominate everything. And the web became this thing, this almost a god in the way we thought about everything that had to do with software. And so did the database. Anybody remember the ads that these guys put on the air back at the height of the web? The power that drives the internet? And I would sit there and watch that and go, what the hell are they talking about? The database is not the power that drives the internet. But they said so. And then the platforms begin to proliferate. We had J2EE, we had Java, we had Ruby, we had .NET grow out of, you know what .NET is. Do we have any .NET programmers in here? Yeah? Java programmers is what you are. The .NET is really just Java. They changed a couple of letters around and replaced a keyword with a colon. The two have gone in slightly different directions since then, but you can still take some Java code and some C# code and lay them side by side and not see a single bit of difference. And the frameworks proliferated, all the horrible frameworks, DJBs and JSFs and Apache and Wickets and JPA and Struts and Velocity. And we're still in the throes of this because there's a new framework every week and every month. And our outlook has changed. We used to be poised. We had the design patterns, we had the process, we had the design principles, we had all of that. And now we're looking for the next big framework to help us. Now we're looking for the next big tool to help us. If I ask someone, what is the architecture of your system, they're almost certainly going to tell me something like, it's Apache and Spring and some dependency injection and Oracle. And that's not an architecture. That's a bunch of tools. And so came the end. of design and architecture. Since then, we've been putting the pieces together, doing some integration with frameworks and stuff. What happened? Well, the years went by. A decade. And all of a sudden, wait a minute. The web is not an architecture. The web is an I/O device. The web is an I/O device. And what do we know about I/O devices? What did we learn in the 60s about I/O devices? You want to be independent of them. That's why we created device independence. That's why in early Unix there was standard in and standard out. We didn't want to know what the device was. We just wanted to be able to say, well, output this to something and not know what it was. The web is an I/O device that we want to be independent of. And we began to realize the database is not a god. The database is not the center of our system. Our applications are not little minions that serve the desire of the great database in the sky. Our applications rule the database. In fact, the database is an I/O device. Something we want to be independent of. And so we began to remember the design, and we began to remember the patterns, and we began to remember the architecture, and we began to remember what all this stuff was about that we were so enthralled with in the late 80s and the 90s. It's taken a decade, but it's starting to come back to us. We're beginning as an industry to remember, oh yeah, there is such a thing as actually designing and architecting applications. Now, of course, we do this in the context of an agile process, but is there any reason you cannot design and architect something while you are working in short iterations, while you are writing tests, while you are doing all of the things we do in an Agile? Is there any reason that you cannot do this design? The answer to that is, of course not. You can do the design. Is there any reason that you should not begin every iteration with a design session? No, there's no reason why you shouldn't do that. Why wouldn't the team go to a whiteboard and start drawing some simple diagrams? You don't have to spend weeks at it. Back in the days when we were doing the Agile Manifesto, the thing we decried was big upfront design. We did not decry upfront design. Little bits of upfront design aren't a bad idea. And by the way, if you're going to put together a large application, it's probably worthwhile taking a week and thinking about what the heck the shape of that application really is. You don't have to spend months at it. You don't have to design it down to the last little detail. But it would probably be a good idea to know what the general shape of the application is. This will be incorrect, but that's okay, because you can fix it in process. That's what Agile is good about doing, allowing you to fix things as you go along. To have the initial starting point would not be a bad idea at all. Jakobson gave us use cases. This is what a use case should look like. It's simple. It's idealistic. It doesn't really say much. This one says, in order to run this system, you're going to have to be able to create an order. And in order to create an order, well, you need a customer ID. I'm not going to tell you what's in the customer ID. I'm not going to try and give you that kind of detail right now. It's just that I know we're going to have some kind of customer ID. And we're going to have a shipment destination. Don't know what's in that destination. Don't know the form of it. It's okay. We'll get there later. Right now, all I know is that we certainly need a shipment destination. And we need payment information. And we need customer contact information. And we need a shipment mechanism. But I'm not going to tell you the details because I don't know them. And how does the use case work? Well, it's kind of a simple thing. And in rough terms, the order clerk issues a create order command with the above data. That's the first step of the use case. Second is the system validates all the data. I'm not going to tell you how. I don't know what the validation rules are. I'm not going to write them down here. We'll do that later. I do want to say, though, that we are going to validate the data. And then the system creates the order and determines the order ID. I don't know how. That's probably a database operation, but I'm not going to say that right now. And finally, the system delivers the order ID to the clerk, probably on a web page somewhere, but I'm not going to say that. Is this a web system? It could be. There's no reason why it couldn't be, but I'm not going to say that here. There's nothing here about the web. Why? Because we want to be independent of the web. Are we using an Oracle database? Are we using a relational database? Don't know. Don't care. Not important. I can specify the use case. I can capture the essence of the business rule without knowing whether we're on the web or whether we've got a relational database. I don't need to know those things. How much work can you do without having to know those things? The answer to that is you can do a lot without having to know what database you're using or whether it is even a relational database. Whether it's on the web or not, the web is not important to these kinds of decisions. Jakobson said, if you've got a use case, you can turn it into an object. There's an object. I call it an interactor. An interactor is a simple object. It captures the essence of the use case. The code inside this object follows the decisions and the procedures inside the use case. I call it an interactor because Jakobson called it a control object. And I didn't want it to collide with model view controller, so I changed the name to interactor. The interactor contains application-specific business rules. And now I need to explain something. There are two kinds of business rules. First kind of business rule, application-specific. And that means that this business rule cannot be used in another application. Then there are application-independent business rules. These are business rules that apply to many applications in the same domain. So imagine we've got an order entry system and an order processing system. The use case, create order, only applies to the order entry system. But the algorithm for computing the price of the order very likely goes in both of those applications. So one of them is application-specific, one of them is application-independent. The application-specific stuff goes into the interactor. The application-independent stuff goes into what Jakobson called entities. Nowadays, we would call these business objects, but we would be wrong, because a business object in most of our worlds mixes the application-specific and the application-independent stuff. In this case, the entity is a pure element of the domain model, knowing nothing about the application, but knowing about the domain instead. And it is the interactor's job to control the dance of the entities. So the interactor tells the entities what to do. Jakobson had one other kind of object. He called it the boundary object. And I've shown them here as interfaces. If I had time, I would rant about interfaces. I might just have time, but not yet. Those are interfaces, or I should say abstract classes. Those are abstract classes or interfaces. Notice that one of them is used by the interactor, one of them is derived from by the interactor. The interactor derives from the one on the bottom. It uses the one on the top. The one on the top is the output boundary. Anything going out of the interactor goes out through that boundary interface. Anything coming into the interactor goes in through that bottom one. Notice that the two dependencies point in the same direction. That's really important. That's what we call architecture. Yes, there'll be more. Now, let's walk through this. We've got a delivery mechanism on the left over there. It's some user's going to talk to it. By delivery mechanism, I mean the web. Well, it might be the web, might not, I don't know. It's just some UI. But it's going to talk through the boundaries to the interactor. The interactors will control the entities. Watch how this works. The user pushes a button or enters some data or something, and the delivery mechanism's job is to create a data structure that represents the use case, the data going into the use case. This data structure I call a request model is a pure data structure. It doesn't know about the web. It doesn't have any trappings of the web. It's not the little parameter thing that you get in an HTTP request. It's a raw data structure. If you're programming in .NET, it's a plain old C# struct. If you're in Java, it's a Java object with probably public data elements. It's not an object, it's a data structure. That data structure gets passed through the boundary object into the interactor. The interactor looks at it and says, well, okay, I guess they want me to do something, and it pulls the data out of the request model, and it uses that data to control the dance of the entities. Tells the entities to do things based on all that data. And then the flow gets reversed. All the data comes back out of the entities, is gathered by the interactor, and the actor produces a result model. Result model is another data structure. Plain old data structure. No trappings of the web, has no idea where it's going. That data structure goes back out through the boundary objects through the delivery mechanism where it somehow by magic gets displayed to the user. Can you test that interactor? Yeah. You create the request model, you hand it to the interactor, you look at the result model in your test. You can test the interactor. Do you have to have the web server up to do that? Do you have to have the web server running to test the interactor? No. Do you have to have the database running to test the interactor? Well, we don't know where the entities came from. Maybe they came out of the database. Well, we'll talk about that in a minute. But you don't have to have the web running anyway. You don't have to have the application server running. If you're very, very clever, you could run these tests on your laptop without any web server running, without any connections to any databases, without anything. Just run it on your laptop at 30,000 feet while you're flying over the Atlantic. This is the test of a true test. A true test does not need to be connected to anything, and you can run it at 30,000 feet over the Atlantic while sipping a gin and tonic. Yes, there'll be more. What about model view controller? I thought that was the architecture we all used. Anybody know this guy? Wait, he's not up there. Hold on. That guy. Anybody know that guy? I'm going to completely butcher his name. When I say it, it sounds like this. Trygve Renskaug. I don't know if that's right or not, but I met him once. And it was in Oslo. And I was giving a talk, and I was up in the speaker's lounge preparing, and in walks Trygve Renskaug. Yeah, now, I'd read about him since I was, little. And I was in the midst of trying to find a place to plug in my laptop when he walked into the lounge. And he saw my dilemma, and he picked up a power strip, and he handed it to me. And I graciously took it from him, and our fingers touched. I haven't washed that hand. Trygve Renskaug came up with this idea a very, very long time ago in probably the late 70s. And it's a simple idea, a model view controller. We begin with a model object. Model object is just a crystallized business rule, really, really small one. It does not know how it is output. It does not know how it's input. It's just a processing engine. The controller down there at the bottom is an input engine. It gathers input from some source. Maybe it's the keyboard, maybe it's the mouse, maybe it's some service-oriented architecture interface, God help you. But whatever it is, the input comes in through the controller. The controller tells the model what to do with that input. The controller gives commands to the model at the level of the model. And then the model has views. That funny little arrow up there is an observer relationship. The views register with the model. The model calls back to the views. So whenever anything changes in the model, the views are notified, hey, something changed, and the views go look inside the model and display it any way they wish. Simple idea, input, process, output. When we did this in the early 80s, we would have a model view controller for a button, and another one for a text object, and another one for a checkbox, and another one for a little edit box. These were small things. We did not have a model view controller for the whole screen. We had a lot of little model view controllers. Then came the web. And the web did that. Got the web over there to the right. It's going to do some fancy-dancy processing on HTTP requests. It'll run them through some kind of router algorithm and eventually tell the controllers, here, controller, you, deal with this. The controller then unpacks the HTTP request, and then it reaches into this vast sea of business objects and starts to manipulate them. And then it hands control over to the view, and the view reaches back into the vast sea of business objects and gets data out of them and then displays the data. And the problem with this is there's no boundaries. The boundaries are fuzzy. There's no control over the dependencies here. And by the way, the dependencies that we do have go the wrong direction. And so the business objects begin to acquire controller-like features. And they begin to gather view-like features. And worse, the controllers begin to gather business object-like features. And the views begin to gather business rules as well. There's a blurring of the division. What you're looking at there is a boundary, that double black line. That's an architectural boundary. Notice that the dependencies crossing that black line all go in one direction and point towards the business rules. They point inwards. And they land on things that are abstract, like the boundary object or the data structure. Now, here's how this works. The interactor has just created the response model, the result of a computation. It's going to pass it out through the boundary object to a presenter object. The job of the presenter is to organize the data within the response model so that it can be displayed by whatever mechanism is supposed to display it. In the case of the web, the presenter would gather all the information from the response model and organize it into strings. If, for example, you needed to display money, there would be a money object in the response model, but in the view model being created by the presenter, it would be a string. If it had to have 2 decimal places of accuracy, it would be the presenter that trimmed it out and rounded it and did everything necessary and put it in a nice little format. If it needed a little euro sign in front of it, it would be the presenter that put that little euro sign in front of it. If you had a date that needed to be displayed, the date on this side and the response model would be a date object. But over here in the view model, it would be a string already formatted by the presenter for however it was supposed to be displayed. If you have menus, it is the presenter that figures out the names of the menus. If some of the menu items need to be grayed, the presenter creates Boolean flags so that the view knows which ones to make gray and which one doesn't. Anything that appears on the screen is first created by the presenter in a screen-independent way, and then it's displayed by the view. Look at the view down here. It's this fuzzy little thing you can barely see. That's because there's almost no code in it. All the work has been done by the presenter. Can you test that presenter? Create a response model, hand it to the presenter, look at the view model. Do you have to have the web running to test the presenter? No. You can test the whole thing. You could test all your business rules, all your presenters, without having the application server running, the web running, anything running, at 30,000 feet while sipping a gin and tonic. And of course, you can do the same thing to the database. You can create another architectural boundary that isolates you from the database. Using the same technique, all the dependencies point upwards. You've got an interface at the business model level that knows what all the queries are, names them as functions. The business rules call those functions. They're implemented below the line and talk to the database. The only part of this code that knows the database is even relational is the stuff below the line. If you're using Hibernate, who's using Hibernate? That's below the line. That's not above the line. In fact, you take real care with this stuff inside those black lines, because that's the family jewels in there. Those are the business rules. That's the real reason you're doing this application. You don't let things like the database in there. You don't let things like frameworks in there. The stuff in there doesn't know about SQL, doesn't know about Spring, doesn't have little @AutoWired sprinkled all over it, doesn't know that you're using framework X or framework Y. The stuff inside the black lines you keep pure, because that's the essence of what you're trying to create. And that's the end of my talk. Are there any questions?